Hey everybody, here is 2011 AP Physics C question number 2. Alright, so on the dot that represents the passenger compartment, draw and label the forces, not the components, that act on the compartment when it is at point C. All we're worrying about is the forces. Remember, it's frictionless from A to D, so we got gravity pointed straight down, and then at this point, point C is right there, so we're going to have a normal force coming off at that type of angle. So we're just going to add that to our diagram here. There's our normal force. And that's it, guys. Those are the only two forces acting on it. So we've got some points here. 1 point for this one, 1 point for that one, 2 points on that problem. All right. Moving on to part B. In terms of theta and the magnitudes of the forces drawn in part A, determine an expression for the magnitude of the centripetal force acting on the compartment at point C. Okay, so the centripetal forces are the forces that are pointed towards the center. All right, so at this point right here, obviously, normal force is pointed towards the center. But we're also going to have a component of the force of gravity pointed towards the center here. So we need to account for that. Now, we want to make sure that we redraw this by itself. So I'm going to come down here and do this over here. All right, so for part B, let's go ahead and redraw our force diagram. So we're going to have force of gravity going down. We're going to have normal force right here. Now, our angle theta is this angle right here. Now, our coordinate plane that we have is going to be the radial direction here and the perpendicular direction right here. All right. So what we want to find out is we need this component of the force of gravity. There's a right angle. So we want what is the radial component of the gravity. Now this angle theta is going to pop up down there. So that means that this force of gravity in the radial direction is going to be equal to mg sine of theta. All right. So if we're looking for the centripetal forces, the forces in the centripetal direction, we're going to have normal force minus mg sine of theta. All right. And all it was asking us for here, guys, was the centripetal forces. Okay. That's all we need to do here. So this part B was 1 point, and you get 1 point for the correct expression of those forces. The hard part here is obviously getting it split into components. Just make sure that you've got that angle in the right spot. All right. Part C says derive an expression for the speed of the passenger compartment as it reaches point D in terms of m, r, and the fundamental constants. All right. So easiest way to do this, guys, is with conservation of energy. So part C, conservation of energy. Let's start off by looking at the energies that it has at point A. At point A, it's all potential. So that's potential energy at A. At point D, it's all kinetic. Don't want that. It's all kinetic at point D. All right. So this makes a expression real easy. We can say that energy at the beginning is equal to the energy at the end. So we have the potential energy due to gravity at the beginning is equal to the kinetic energy at the end, which is just going to be mgh initial is equal to 1/2 mv final squared. Now I just need to solve this equation for v. So this is going to be 2 mgh initial divided by m square root is equal to v final. So if we plug some things in here, our height, this is what is going to be tough here, the height of this thing. I know that this right here is 3r over 4, so I need to figure out what this height right here is. I know that this right here is r, all right, m times 3r over 4 plus r square root is equal to r, because that m went away there. All right, 7/2 times gr is equal to v final. All right, points here on this one. So you get 1 point for the correct application of the conservation of energy, and then you get 1 point for the correct answer. All right, 7/2 gr there. Oh, forgot the radical on this. Radical, 7/2 gr. All right. Moving on to part D. Part D asks us to figure out if the compartment is brought to rest by friction, calculate the numerical value of the coefficient of friction between the compartment and the track. All right, so now we're paying attention to this spot right here from D to E, where we do have some work being done. Now, work energy theorem says that the change in kinetic energy is equal to the work. Well, I'm going from some kinetic energy to no kinetic energy. Therefore, my final kinetic energy is 0. My initial kinetic energy, I just solved for, is going to be equal to my work done here. Now, this is going to be negative 1/2 mv initial squared is equal to the work, and work is force times displacement. Now, the force here is the force of friction. The force of friction is going to be acting in the negative direction. So this is going to be negative 1/2 mv initial squared is equal to negative mu times the normal force times delta x. All right. Now, what is normal force here? Well, normal force is mg. So make that substitution. Negative mu times mg times delta x. All right. Now, what are we solving for? Well, we're solving for mu. So let's see what I know here. I know what delta x is. It's 3r. I know what m is. I know what g is. I know what v initial is. All right. Let's go ahead and make some substitutions here. Now, v initial I solved for in part C. Over there, it was v final. But now it is our v initial for this situation. So that is going to be radical 7/2 gr. So I'm squaring that. So that's going to become just 7/2 gr. All right. Over 2g. And then that delta x is 3r. All right. So I solve this out. I'm going to get 7/12. All right. 7/12 is going to be equal to mu here. And that would be enough for your answer. So let's look at points on this one. More points on this one. So you get a correct expression for relating the work done by the friction force to the kinetic energy. So that would be 1 point for that. You get 1 point for the correct expression of the frictional force, so 1 point there. And then you get 1 point for the correct substitution of the velocity. So 3 points on that problem. Remember, it's important to show all that work. All right. Moving on to part E. Write but do not solve the differential equation for v of t. Okay. So by this point, hopefully, we are getting real used to seeing this type of expression. So let's look at the sum of the forces. Sum of the forces is equal to mass times acceleration. The forces that are bringing this thing to rest, well, that's going to be our braking force, which is negative kV. So negative kV is equal to mass times acceleration. Now remember, to make a differential, I need the differential version of velocity. So I'm going to say that A is equal to dv over dt. So this becomes negative kV is equal to m times dv dt. All right. And guess what, guys? That's all you need to do on part 1. All right. The points on this one, substituting the braking force in, and then substituting the derivative of velocity for acceleration. All right. Do not overcomplicate that. If it says do not solve, leave it just as that. Make your life easy. Part 2, though, says to solve that differential equation because they're so mean. So let's go ahead and solve that differential. All right. So we got negative kV is equal to m dv dt. Okay. First thing we want to do, we want to separate these variables because we want to get v with dv. Okay. So here's what this is going to turn into. All I did was rearrange that to get things together. Now I'm going to integrate this. All right. So for v, I'm going to integrate this from v initial to v because we don't know what v initial is. And then this, I'm going to integrate from 0 to t because t initial is always 0. All right. Now, over here on this side, this is going to be real easy. This is a constant, so this is just negative km over the integral 0 to t dt. The integral of 1 over x is equal to the natural log of x, right? We got the integral of 1 over v. So over here, we're going to get the natural log of v from v initial to v. And then on this side, we're going to get t from 0 to t. All right. So this is going to be negative kt over m is equal to the natural log of v minus the natural log of v initial. All right. This is going to be negative kt over m is equal to the natural log of v over v initial. All right, we make that little simplification there. And I'm going to do our little verb here, take e to the both sides to get those v's out of that expression. All right, so this is going to be e to the negative kt over m is equal to v over v initial. I get v initial over to the other side, so v initial times e to the negative kt over m is equal to v of t. All right, and there is our expression. Now, shockingly, guys, this is only worth 2 points. All right, so you get 2 points for separating the variables and integrating, and then you get 1 point for the correct expression. All right, so if you can literally just get it separated, you're solid. All right, now moving on to the final part, part 3. On the axes below, sketch a graph of the magnitude of the acceleration of the compartment as a function of time. On the axes, explicitly label any intercepts, asymptotes, max, min, with numerical values or algebraic expressions. Okay, so we're looking at acceleration here. Now, what you're going to want to do, guys, is to get like an idea of what this is going to look like, we're going to want to take the derivative of the expression that we just got. So we got this expression for v down here. So I'm going to take the derivative of this to get an idea of what our acceleration is going to look like. So if I do this, let's make this part 3. So I've got v of t is equal to v initial e to the negative kt over m. All right, so I'm going to say dv dt is equal to d dt of v initial e to the negative kt over m. All right. So if I take the derivative of this, v initial is a constant. Taking the derivative of e, so dv dt is going to be equal to v initial times d dt of e to the negative kt over m. All right. This is going to end up becoming v initial times, we're going to take the derivative of the exponent there, so that's just going to be negative k over m times e to the negative kt over m. So a of t here is going to be equal to negative v initial k over m times e to the negative kt over m. All right. So we can get an idea of the basic shape of this graph. It's going to be something like this. That's terrible. But it's going to be something like that probably. Okay. But we need to figure out where does this thing start? Okay. So basically, what is this thing at a of 0? So when t is equal to 0, well, this thing becomes negative v initial k over m. All right. So up here, what we're going to do is we're looking at the magnitude of the acceleration. So this is going to be v initial k over m. Remember, it's just the magnitude, so we don't need to worry about that negative sign there. Now, as this thing goes to infinity, so let's look at this. As t goes to infinity, this thing is going to get closer and closer to 0. So our asymptote is going to be at 0, which means that our expression is going to look something like this. And then we want to note that asymptote. So this is going to be an asymptote at 0. All right. 3 points on this problem, guys. Those 3 points come from a finite intercept on the x or on the y-axis. So we need to specify that intercept. That's why we went through all the trouble of the derivative. 1 for it being concave upward, and then 1 for labeling that with an initial value. So even if you didn't know what the intercept was, you got 1 point for at least specifying that there is an intercept, and then you got another point for knowing exactly what it is.